Magnetic field due to a solenoid carrying current. A solenoid is an electromagnet. A solenoid is an electromagnet which consists of an insulated wire, which consists of an insulated long wire closely wound in the form of a helix. A solenoid is an electromagnet which consists of an insulated long wire closely wound in the form of a helix, such that its length is very large as compared to its diameter. This is a diagram of a solenoid, and the horizontal dotted line is the axis of the solenoid. D is the diameter of the solenoid and L is the length of the solenoid. In this case, D is much less than L, means diameter of the solenoid is much less than its length. It is used to generate a controlled magnetic field. It is coined in 1823 by Ampere. It is coined in 1823 by Andre Marie Ampere. It is to generate a controlled magnetic field, and it is coined in 1823 by Andre Marie Ampere. It can also be used as an electric. In diagram, we have a solenoid. X and Y are the two ends of the solenoid. A current I flows through the cylindrical coil in this way. Current enters into the solenoid through the end X, and it will flow away from the end Y. And small l is the length of the solenoid. And we consider a point P on the axis of the solenoid. P is a point on the axis of the solenoid, and at P, a magnetic field B will be acting towards right, means towards the end Y. So this is the direction of a magnetic field B. Which acts along the axis and towards the end Y. And we have a number of turns, and we can consider a rectangular closed path. Partly inside the solenoid, partly outside the solenoid, and the rectangular closed path is ACDG, which touches the axis of the solenoid as according to the diagram, and this is the closed path, rectangular. At the point P, we can denote the direction of magnetic field B. B is a magnetic field which acts at the point P towards the end Y and inside the solenoid. And there will be a current flowing through the turns in this way. There will be n number of turns of the solenoid through which a current I will be flowing, and n prime number of turns enclosed by the closed path ACDB. Let I be the electric current which I be the electric current which is flowing through a long solenoid. I be the electric current which is flowing through a long solenoid xy of length small l and number of turns capital N from the end x to y such that the index of the solenoid xy carrying current I gets magnetic south pole or S pole, This is the south pole which is induced, magnetic south pole which is induced at the index, and magnetic north pole, that means N pole, is induced at the other end y of the solenoid. Magnetic south pole is induced at the end x, and magnetic north pole will be induced at the other end y of the solenoid. Let us consider a rectangular closed path. A rectangular closed path ACDG. In the diagram we can denote ACDG as a rectangular closed path. This is the closed path ACDG. Let us consider a rectangular closed path ACDG. Let us consider a rectangular closed path ACDG. We can draw the solenoid. Let us consider a rectangular closed path. ACDG. Which is considered partly inside the solenoid, touching. So now we can denote the rectangular closed path. This is the rectangular closed path ACDG. Partly inside the solenoid, touching the axis of the solenoid as one of the side AC, and partly outside the solenoid, and an insulated wire is wound on this cylindrical core. I be the current which is flowing through the solenoid. This is the current I. Small l is the length of the solenoid and capital L is the length of the side AC. And partly outside the solenoid such that small l less than capital L is less than small l, where capital L is the length of the side AC of the rectangular closed path. Length of the side AC and the current I will be flowing through the rectangular closed path, through the plane of the rectangular closed path ACDG normally. So in the diagram we have this type of turns passing through the plane of the rectangular closed path ACDG, and P is a point on the axis of the solenoid, and at P magnetic field B will be acting along the axis. Magnetic field B acts along the axis, and these are the turns. And here we can denote the direction of current. Current I will be flowing downwards through the turn, and in this case we can denote the direction of current at the highest point of the solenoid, and this current will be acting outwards, and it will be passing through the plane of the rectangular closed path normally. This current I will be passing through the closed path normally. Now B is the magnetic field induction. At the point P on the axis of the solenoid, B is the magnetic field induction at the point P on the axis of the solenoid, which acts along the axis full stop. According to Ampere's circuital law, the line integral of the magnetic field induction B along the perimeter of the rectangular closed path ACDG, ACDG is closed integration vector B dot vector dl ACDG, vector B dot vector dl equal mu 0 n prime I under bracket n prime I, where n prime is the number of turns. N prime is the number of turns passing through the rectangular closed path ACDG. N prime is the number of turns passing through the rectangular closed path ACDG. Now we can draw the diagram. This is the solenoid. We can draw the diagram again. An insulated wire is wound in cylindrical form on this cylindrical core. So I be the current which is flowing through the rectangular solenoid, and this is the axis of the solenoid, and we can consider a rectangular closed path. This is the rectangular closed path which to be considered partly inside the solenoid. ACDG is the rectangular closed path, and this will be the direction of current passing through each turn of the solenoid I. Small l is the length of the solenoid. N, capital N, is the total number of turns of the solenoid. 1, 2, 3, ... Last turn is N. Now the length of the part AC is capital L. 1, 2, 3, ... N prime, and N prime is the number of turns of the portion AC. N prime is the number of turns of the portion AC, or the number of turns passing through the rectangular closed path AC dg. Now at P, magnetic field B acts along the axis from south pole to north pole inside the solenoid, or closed integration vector B dot dl A to C, from A to C, closed integration vector B dot dl, then integration vector B dot dl from C to D, that is from C to D along CD, it is integrated, plus integration D to G vector B naught dot dl, where B naught, vector B naught is a magnetic field induction acting outside. So at this point, magnetic field induction is V0, which is acting from D to G along DG, as shown in the figure. B0 is a magnetic field induction which is acting outside the solenoid B0, and this B0 will be acting along DG. Then integration G to A vector B dot vector dl is equal mu 0 n prime I, where n prime is the number of turns of the portion AC. Close integration A to C B dl cos 0 degree, integration C to D B dl cos 90 degree, integration D to G B naught dl cos theta, not 0 degree, it should be cos theta, because theta is the angle between B naught and dl, integration G to A B dl, integration, in the next line we can write integration G to A B dl cos 90 degree equal mu 0 n prime dot I, where n prime dot I is the current, total current, which will be threading the rectangular closed path normally. This is the rectangular closed path, and we can draw the diagram of solenoid. This is the cylindrical solenoid. So an insulated wire is wound in this way in a form of cylinder or helix. We can draw the axis of the solenoid. This is the axis of the solenoid, and we can complete the rectangular closed path. So AC DG is the rectangular closed path, which is assumed partly inside the solenoid, partly outside the solenoid. At P, magnetic field induction B acts along the axis, and small l is, capital L is the length of the portion AC, or length of the rectangular closed path, vector B dot vector dl from A to C. From A to C, here integration B dl cos 0 degree. Vector B acts from A to C, and we consider a small length along AC, that is vector dl will also be acting along AC. That's why vector B is parallel to vector dl, and here hence vector dl, integration dl is capital L, because length of the portion AC, integration d small l is equal to capital L from A to C. Now integration A to C B dl cos 0 degree is explained in this way, and integration C to D vector B dot vector dl is integration C to D B dl cos 90 degree, because from C to D we consider a small length dl, small element length dl, and vector d acts along the axis. So vector dl is perpendicular to vector B. From C to D, vector B acts along the axis, so that's why vector B is perpendicular to vector dl, and theta is equal to 90 degree. Theta is equal to, from D to G, at a certain point we consider a small element of length dl, at this point, and B0 is the magnetic field induction along dg. B0 is the magnetic field induction along dg outside the solenoid. So then integration a to c b dl plus 0, second term will vanish. Integration d to g b naught dl cos theta plus 0, that is integration. So here we get cos 90 degree and also cos 90 degree from g to a, mu 0 n prime dot I. Now integration a to c b dl plus 0 equal to mu 0 in prime I, where B0 equal to 0, which is the magnetic field induction at a point outside the solenoid. Magnetic field induction at a point outside the solenoid is 0. Is the magnetic field induction outside the solenoid, which is 0. That means no magnetic field induction acts outside the solenoid. Now we can bring B outside dl. B integration a to c dl equal mu 0 n prime dot I. Integration or B into capital L equal mu 0 n prime I, where L is the length of the portion AC. Length of the portion AC of the rectangular closed path. Integration a to c d small l is equal to capital L, and where capital L is the length of the portion AC of the rectangular closed path AC dg, rectangular closed path AC dg. Now if we draw the diagram of the solenoid again, this is the axis of the solenoid and rectangular closed path AC dg. AC dg, small capital L is the length of the portion AC, small l is the length of the solenoid, small b is the breadth of the side CD, length of the side, dl is the length of small element. So from to x to y, integration a to c dl is capital L, and integration x to y dl is equal to small l. Mu 0 n prime by capital L into I. Therefore, B equal mu 0 small n I. B equal mu 0 small n I. This is the magnetic field induction or magnetic flux density at a point inside a long solenoid carrying a current I. Magnetic field induction or magnetic flux density. Magnetic flux density at the point P on the axis of the solenoid, on the axis of the long solenoid. It should be long, not a solenoid of finite length. Axis of the long solenoid of infinite length carrying current I. And this magnetic field is acting inside the solenoid, not outside the solenoid. This magnetic field induction, acts from south pole, S pole of the solenoid, to its north pole, N pole. And it acts inside the solenoid along the axis. Along the axis of the solenoid and inside the solenoid. Magnetic field induction acts from south pole to north pole. So this is the solenoid. We can draw the diagram of solenoid and axis of the solenoid. P is the point at which magnetic field B acts towards right. Magnetic field B, vector B, acts towards right. Insulated wire is wound in a form of cylinder. I be the current flowing through the solenoid, and this is magnetic south pole and magnetic north pole induced on the ends X and Y. Vector B is the magnetic field induction which acts from south pole to north pole along the axis and inside the solenoid, where N is equal to n prime by capital L, capital N by small l, which is the number of turns per unit length of the solenoid. Number of turns per unit length of the solenoid. N prime is the number of turns of the portion AC having length capital L, and N is the total number of turns of the solenoid having length small l. Again, we can draw a diagram of solenoid. Rectangular closed path, insulated metallic wire is formed in this way, in a form of cylinder or helix. I be the current flowing through the solenoid, and this is the direction of current I flowing through each turn of the solenoid. AC and X and Y be the two ends of the solenoid. ACDG is a rectangular closed path. N prime is the number of turns of the portion AC. Capital L is the length of the portion AC. Capital N is the number of turns of the solenoid, and small l is the length of the solenoid. Now, hence N equal to N by L. From X to Y, small n is N by L, which is the number of turns per unit length of the solenoid. Again, from A to C, small n, from A to C, small n equal N prime by capital L. This is also be the number of turns per unit length of the solenoid. N equal to N prime by L, N prime by capital N, and again N equal to capital N by small l. We can find the number of turns per unit length in this way, in following two ways. One is N by L, another is N prime by capital L. So this is the number of turns of per unit length of the solenoid, number of turns per unit length of the solenoid. Additional information: magnetic field induction. Magnetic field due to a current carrying solenoid of finite length. Initially it was a solenoid of infinite length. Now you are considering the magnetic field due to a current carrying solenoid of finite length. We can draw the diagram of a solenoid of finite length. This is the cylindrical core of the solenoid, and this will be the axis of the solenoid, and that is imaginary. It is denoted by dotted straight line. X and Y be the two ends of the cylindrical solenoid. We consider a point P. At P, magnetic field B acts towards right. From south pole to north pole. Now we can connect X and P, oblique distance of the end X from P, and again we can connect P to Y, that is the oblique distance of the end Y. Py be the oblique distance of the end Y from the point P. An insulated metallic wire is wound in this way, in the form of cylinder or helix, and I be the current flowing through the solenoid, and this are the direction of current flowing through each turn, and that will be flowing downwards. Magnetic south pole will be induced on the end X, and magnetic north pole will be induced on the end Y. The angle subtended by the oblique distance xp with the axis is theta 1, and angle subtended by the oblique distance yp with the axis is theta 2. Capital N is the total number of turns of the solenoid, number 1, 2, 3, ... and nth turn of the solenoid. Small l is the length of the solenoid. Now we have to know the expression of magnetic field induction, that is the expression of B at P. At P, B has the expression 1 by 2 mu 0 small ni under bracket cos theta 2 minus cos theta 1, cos theta 2 minus cos theta 1, where small n is the number of turns per unit length, where small n is n by L. So B equal half mu 0 ni cos theta 2 minus cos theta 1. That is the magnetic field induction, or magnetic flux density. Magnetic flux density at the point P on the axis of the solenoid of finite length. If we consider the angles theta 1 and theta 2, so that solenoid should have finite length. It acts from S pole to N pole inside the solenoid. S pole to N pole and along the axis inside the solenoid. Magnetic field B acts from south pole to north pole. Magnetic field B acts from south pole to north pole, where theta 1 and theta 2 are the angles subtended by the oblique distance of the two ends x and y with the axis x and y of the solenoid at the point on the axis of the solenoid. Another additional information, we can draw the diagram of solenoid again. So this is the circular cross section of the solenoid. In this way we can draw the diagram of solenoid, and this is the axis of the solenoid. Dotted straight line is the axis of the solenoid. P1 and P2 be the two ends, two centers of the circular cross section at the end x and y. P is a point on the axis. And if P coincides with P1, that means the point of observation is P1. In this case, the oblique distance of the end y from the point P1 makes an angle theta 2, and the oblique distance of the end x from the point P1, so that is xp1 is the perpendicular distance of the end x from the point P1. This is the perpendicular distance. So oblique distance P1y of the end makes an angle theta 2 with the axis, and the oblique distance, perpendicular distance of the end x P1 is theta 2. At P1, theta 2 approximately equal to 0 degree due to a long solenoid. For long solenoid, the end y will be at infinite distance, and the oblique distance P1y will be almost parallel to the axis, and B equal half mu 0 ni cos theta 2 minus cos theta 1, half mu 0 ni cos 0 degree minus cos 90 degree. Therefore, B equal, it can be denoted by B end equal half mu 0 ni. So this is the magnetic field induction, and at the end P1, magnetic field induction B end will be acting along the axis and inside the solenoid, and that will be acting from magnetic south pole to north pole induced on the solenoid. B end equal 1 by 2 mu 0 small n capital I is the magnetic field induction at the end P1 of a long solenoid, at the end P1 of a long solenoid. Again, we can draw the diagram of solenoid x and y be the two ends, and at P magnetic field B will be acting along the axis towards right. We can denote the oblique distance. We can denote the oblique distance of the end x and oblique distance of the end y from the point P. This can be denoted by dotted straight line. These are the two oblique distance of the end x and P, and B is the magnetic field induction. Oblique distance xp makes an angle θ1 and oblique distance py makes an angle θ2 with the axis and an insulated wire is zoomed in this way. I be the current flowing through the solenoid. Now at P, the expression of magnetic field induction is 1 mu 0 1 by 2 mu 0 small n small n capital I cos θ2 minus cos θ1. This is the magnetic field induction at P due to a solenoid of finite length. But if the solenoid has infinite length, that means due to a long solenoid, the end x and y will be at infinity, and both the oblique distance xp1, xp and yp will be parallel to the axis. Here θ1 will be 180 degree, the oblique distance will be opposite to the axis, and θ2 will be 0 degree, means the oblique distance py will be parallel to the axis. Therefore B equal 1 by 2 mu 0 ni cos 0 degree minus cos 180 degree. 1 by 2 mu 0 small n capital I 1 minus under bracket minus 1 bracket closed. This will be third bracket. So we get the expression of magnetic field induction at a point inside the solenoid of finite length. Therefore B equal 1 by 2 mu 0 small ni into 2. Therefore B equal to mu 0 small n capital I. This is the magnetic field induction at a point P inside a solenoid of finite length. Magnetic field induction at the point P, on the axis and inside of a solenoid of finite inside of a long solenoid. So hence if we divide B end by B, we get half mu 0 ni divided by mu 0 ni. Therefore B end is equal to 1 by 2 B. B end is equal to 1 by 2 B. Now we can draw the diagram of solenoid again. This is the axis of the solenoid, a point P, and the center P1 of the cross section. At P, magnetic field induction is B, and which acts from south pole to north pole. At P1, magnetic field induction is B, and which is also acting from south pole to north pole inside the solenoid. Insulated wire is wound on the cylindrical core. I be the current flowing through the solenoid. I be the current. In this case, B and magnetic field induction at the end P1 will be half of the magnetic field induction at the point P. We can draw a diagram of a turn. Current will be flowing, I will be flowing upwards with respect to the rear view or rear face, back face of the turn, and this is the rear view of the turn. Rear view of the turn, and this is the front view of the turn. Front view of the turn. magnetic field induction at the center of the turn, current I will be flowing downwards with respect to front view, and at the center of the turn, magnetic field B will be acting towards right, as according to right hand thumb rule or right hand palm rule, magnetic field B will be acting towards right if current flows downwards with respect to front view and current flows upwards with respect to rear view. If current flows downwards with respect to front view, according to right hand thumb rule, magnetic field vector B will be acting towards right. Magnetic field B will be acting towards. Hence, magnetic field B will be acting towards right at a point P inside the solenoid.